So in this section, we'll present this fundamental theorem of calculus. So this is the central theorem, you guys, of integral calculus. It connects integration and differentiation, enabling us to compute using an antiderivative of the integrand rather than just by taking the Riemann sums as we previously did. So Leibniz and Newton, they exploited this relationship and started the mathematical developments, that fueled or spearheaded the scientific revolution over the next 200 years, right? So Newton and Leibniz discovered or invented, depending how you look at it, calculus in about 1665 to 1617 independently. And so we'll also present in this section an integral version of the mean value theorem, which is another important theorem that's used to prove this fundamental theorem. Okay, so let's get started. So we have the integration from a to b is equal to the antiderivative at b minus the antiderivative at a. So let's do a simple example here. And by the way, some textbooks will call this the fundamental theorem of calculus part 2. That's it. So you'll hear both. Others call it this first fundamental theorem of calculus. And if you remember from last time, we ran this limiting process and we realized, oh, it's the integral, right? And so as long as the function is positive, like in this case, from 1 to 3, you see over here from 1 to 3, see how this function is positive right here? So this integral will be finding our area right there, shaded for us. So let's go ahead and let's run it. Let's run the integral. So I got negative 3x to the 3 over 3 plus 12x to the 1 plus 1 is 2 over 2 minus 9x from, so I'm going to put that little notation, from 1 to 3. So instead of a plus c here, we're saying, hey, it's from 1 to 3. So I got to plug in. Well, let me clean this up a little bit. I got negative x cubed plus 6x squared minus 9x from 1 to 3. So if you notice, I plugged the b in first. That's the, we're going from a to b here. So I plug the 3 in first. That's this part. And then minus, and now I plug the a part in. Minus, and now I got to plug the a in, which the a is 1. There's our a. I got 16, I got 54 minus 27. Minus, I got negative 1 plus 6 minus 9. And so notice I got negative 54 plus 54, so that's gone. And then I got a negative 1 plus 5 minus 9 is a negative 4, so I got negative 4, which is a positive 4. So that's actually our area. That's not only the answer to the integral, the definite integral, it's also the area, because it's above the x-axis. So that area right there under the curve, we just found to be 4. My goodness, that's so much easier than that limiting process that we were running, right? So now we can use this. Let's do another one here. Notice, though, that this time, this function graphed over here on the right from negative 2 to negative 1, right? So from this negative 2 to negative 1 there, see how the curve it's underneath? And so when it's summing all these up, which the integral is doing, right? It's summing up all these infinite amount of rectangles, summing all these up. Well, the height of the rectangle is the functional value. Well, the function value is negative. So it's a negative height, if you will, times the width, and then it's summing them all up. So it's going to give you the opposite, or a negative value. Like, let's say this negative, it ends up being negative 7. Well, the area is not really negative 7. The area is positive 7. It's the opposite of that because it's below the x-axis. okay, is what this integral will be doing. Let's go ahead and run the integral, though. We've got the integral of u minus u to the negative 2 du from negative 2 to negative 1. So we got u squared over 2 minus u, negative 2 plus 1, negative 1 over that negative 1 from negative 2 to negative 1. So I got u squared over 2. Take that negative up top, I got plus 1 over u. Now let's throw the negative 1 in. Negative 1 squared over 2 plus 1 over negative 1 minus, now I throw the negative 2 in. So I got 1/2 minus 1 minus, looks like I got negative 2 squares, 4 over 2, which is 2 minus 1/2. You come over here, I got 1/2 minus 1. Let me distribute that. Minus 2 plus 1/2. 1/2 plus 1/2 is 1. Minus 1 minus 2. So I got negative 2. That's the answer to the integral. So if I come back up here, it wasn't negative 7, it was negative 2. So the actual area is 2. It's the absolute value of that. Bless you. This next one here, I'll go ahead. Let's rewrite this before I do that. So I have 3x squared over 3x squared minus, that's x squared to the 1/3, so x to the 2/3 over 3x squared, 1 to 8. So I have the integral of 1 minus 1/3, and then x to the 2/3 minus 2. Well, that's x to the 2/3 minus 6/3, or negative 4/3. From 1 to 8. Now I'm going to run the integral, so constant times x minus, constant stays there, x to the negative 4/3 plus 1. Negative 4/3 plus 3/3 is a negative 1/3, all over negative 1/3 from 1 to 8. And so we've got x, and I've got plus, notice the negative 1/3 over negative 1/3, so that's a plus x to the negative 1/3, 1 to 8, or x plus 1 over the 3rd root of x. Now I plug the 8 in. 8 plus 1 over the 3rd root of 8 minus 1 plus 1 over the 3rd root of 1. So we got 8 plus 3rd root of 8 is 2, minus 1 minus 1 over 3rd root of 1 is just 1. So we got 6 plus 1/2 is 13 over 2. And that's our integral. This next one, you know, if you didn't have the graph, hopefully you're thinking about your transformations. So you take the absolute value of x, you flip it over, so now you're like that, right? Flip the v over, and then you go right 3 and up 3, and so you end up with that graph right there, right 3, up 3 after you flip it over, right? Now, the question is, how do you integrate it? Let me erase this for a minute. Well, if you go back to the definition of the absolute value of x, the absolute value of x is x whenever x is greater than or equals 0, or it's the opposite of x when x is less than 0. So the absolute value of x minus 3, following that, algebraically would be x minus 3 whenever x minus 3 is greater than or equals 0. In other words, x is greater than or equal to 3. Or it's the opposite of that when x minus 3 is less than 0, right? And so you have those two cases. So on the so here, let me write here's your function. You have the first case where you just drop the absolute value, make it into just x minus 3. And this is for whenever x is greater than or equal to 3. So this is the equation, negative x plus 3 plus 3. So you got negative x plus 6. This is for whenever x is greater than or equal to 3. So if you look over here, you see how that's that line, y equals negative x plus 6. And then the other one would be, so you got y, here's our original. Now the absolute value becomes in red, negative, or the opposite of the x minus 3. Well, negative times a negative is a positive. So you got x minus 3 plus 3, which is just y equals x. So here's this part. And this is for whenever x is less than 3, or up until that 3. So that's y equals x on the left-hand side there. So you have two different portions that we've got to integrate. And notice we're going from 1 to 4. So I got to split it up. I got to go from 1 up to where they meet at 3, and then from 3 finally to the 4. So we're going to go 1 to 3 of y being x. And then we're going to add in the 3 to 4, which is on the other blue line, which is negative x plus 6 dx. And that's how we're going to have to do this. Let's go ahead and integrate it. I got x squared over 2 from 1 to 3. Plus, and over here I'd have negative x squared over 2 plus 6x from 3 to 4. All right, let's plug the 3 in. 3 squared over 2 minus, now I plug the 1 in. Over here I got negative, plug the 4 in. Plug the 3 in. So we got 9 halves minus 1 half plus a negative 16 over 2, so a negative 8 plus 24 minus negative 9 halves plus 18. And distribute that. So we got 9 halves plus a 9 halves. That's 18 over 2. That's 18 minus the 18. So those will cancel all that. So I got 24 minus 8 is 16. Minus the 1 half. Sorry guys, I went wrong. 9 over 2 plus 9 over 2 is not 18. It's 18 over 2. So don't cancel that. There we go. 9 over 2 plus 9 over 2 is 9. I'll go ahead and do 20, well, right out here. 24 minus 18, I got 6. So I got 9 minus 8, I got 1, plus 6, 7, minus 1 over 2. 14 over 2 minus 1 over 2, there we go. There's my 13 over 2, my goodness. You know, if I'm looking at this next one, hopefully you're thinking to yourself, remember that sine squared plus cosine squared is 1. So 1 minus sine squared is the same thing as the cosine squared. So this is cosine squared over cosine squared d theta from 0 to pi fourths. Well, that's the same as 1 d theta. And now I run the integral. So it'll be 1x, or in this case 1 theta. So just theta from 0 to pi fourths. And now I plug in the pi fourths for theta minus, now I plug in the 0 for theta. And so we just end up with the pi force on this one. Let's do another one here with the 2 minus cosecant squared. And I would look, if you didn't remember, the integration of the cosecant squared is negative cotangent. So on this one, you can just run it. So it's 2 theta minus the integration of the cosecant squared is negative cotangent from pi force to pi halves. So we got 2 theta plus cotangent theta from pi force to pi halves. So we got 2 theta. I'm going to go ahead and write that as cosine theta over sine theta. And now let me throw the pi halves in. So 2 times pi halves plus cosine pi halves over sine pi halves minus, get this out of the way, 2 times pi force plus cosine pi force over sine pi force. Cosine pi halves is 0, sine pi halves 1. Here we got pi halves. Cosine pi force is root 2 over 2. Sine pi force root 2 over 2. So that's just 1. So I got pi minus pi halves minus 1. So I got pi over 2 minus 1. Right, because this is like a 2 pi over 2 minus pi over 2 is 1 pi over 2. So pi over 2 minus the 1. All right, here I've got the integration of 1 over x minus, I'm going to go ahead and write this as 2e to the 2x. I'm going to integrate these separately. They're both from 1 to 2 here. I know the integration of 1 over x is the natural log of the absolute value from 1 to 2. Minus, now right here I'm going to have to use that u substitution with that. I'm going to let, if you remember, the integration of a to u, a to the u du is 1 over ln of a to the u. Okay. And so I'm going to let my u be that 2x. So du dx is 2. In other words, take the dx to the other side. Du is 2 dx. So I need a 2 and a dx. And notice I have a 2 and a dx. So there's my du. And then the rest of this is just e to the u. And so we have the natural log of the absolute value of x from 1 to 2 minus, now I'm going to run the integral. So it's 1 over ln of e to the u from 1 to 2. But remember, this is x being 1, x being 1 to x being 2. So I got to make sure I put the u back in. And remember, the natural log of e is just 1, so that's 1 over 1. So e to the u is 2x, 1 to 2. So really, since they're both 1 to 2, if you want to, you could put this back. Do it all at once right there. And so you'd have, let's plug the 2 in. Now let's plug the 1 in. Remember, natural log of 1 is 0, so I got ln of 2 minus e to the 4th minus 0 plus e squared. So ln of 2 minus e to the 4th plus e squared. This next one, I would look at my formula sheet, and I would go ahead and use the one that says the 1 over u squared of u squared minus a squared. Du is 1 over a, the arc secant of the absolute value of u over a, plus a constant. That's the one I want to use. Okay. And so if I rewrite this, maybe we can recognize, okay, here's my x. What's being squared? Well, that's 2x is being squared. There's my u. Bless you. So I'm gonna let my u be that 2x right there. And so du is 2 dx. And if you notice, I have right here I have a u. And right over here I also have a u, right? I've got u's in both spots. Well, what's my u? My u is 2x. Well, I've got the u right there, but I need the u right where that x is. So I'm going to give it a 2. There's my u, which means I got to offset it. That's like multiplying by a half, so I got to give it a 2 on the top. So what we have now is 2 over 2x integration of 2x squared minus 1 dx. And let's check out our u substitution. See how du is 2 dx. There's my 2 dx. See how my u right there, and now I'm fitting the form. So I've got u squared minus 1, and a du. And so notice my a is 1, right? So this will integrate. Whoops, what happened? Goodness. So now I'm using the formula, right? So let's go ahead and I integrate it. And don't forget, we are going from a half to 1 over root 3. So I integrate it. It's 1 over a is 1 over 1, arc secant of the absolute value of u is 2x, over a, 1. Normally plus a constant, but in this case it's a defined integral, so we're going, or definite integral. We're going from 1/2 to 1 over root 3. So we've got the arc secant of 2x, both of these are positive values, from 1/2 to 1 over root 3. And so we'll go ahead and throw in, I got 2 times 1 over root 3 minus arc secant 2 times 1/2. And so we've got arc secant of 2 over root 3 minus arc secant of 1. And so the arc secant of 2 over root 3 is pi 6 minus arc secant of 1 is 0. So this just ends up being pi 6. And remember, if you're doing the arc secant, that's saying if the arc secant of 2 over root 3 is something, then is let's say theta, then the secant of theta is 2 over root 3. And so your theta would have to be pi 6, being between 0 and pi, right? So you get that pi 6. And similarly for the arc secant of 1. Hopefully you're thinking on this one, the integral of a to the x is 1 over ln of x. I'm sorry, 1 over ln of a to the x plus c, right? So that's what we're doing here. We've got 1 over ln of 2 to the x, and there's no need to do u substitution because we just have an x up there. This is a definite integral, so we got to plug in 2 minus and then plug in the negative 1. Plug in the negative 1. I'm sorry, plug in the 2. Gosh. Plug in the 2 minus. Now we'll plug in the negative 1. So we've got 2 squared, or 4 over ln of 2 minus, this is 1 over ln of 2, that's 1 over 2 to the 1. So we got 4 over ln of 2 minus 1 over 2 ln of 2. Let's get a common denominator. Let's give this a 2. Now they have a common denominator. So I have 8 minus 1 all over 2 ln of 2. So I guess 7 over 2 ln of 2. Let's evaluate this one here. Notice I do have a picture of it. I'm going from 0 to 1. Some of it is above. You see how it may be hard to tell, but this is a perfect mirror of amount of area on both sides, above and below. So like, let's say this area, maybe this is an area of 2. If this was the exact same amount, the integral from, let's say that's a half to 1, would be like -2. So when you add them up, 2 plus -2, this integral, this whole integral from 0 to 1, is going to end up being 0. So those areas are perfect images of each other. And that's what I'm trying to show here graphically. But let's go through it. So here I've got 1/2 x to the -1/2 minus 3x squared, going from 0 to 1. So I've got 1/2 x to the -1/2 plus 1, positive 1/2, all over 1/2. So I got 1 x to the 1/2, so square root of x minus x to the 3rd, 0 to 1. Let's plug the 1 in. Now let's throw the 0 in. So we've got square root of 1 is 1, minus 1 cubed is 1, minus 0 minus 0. So 1 minus 1, 0. So that's why that area, that's why that integral ends up being 0. Right? This area up here was like 1. This area down here was like -1. So they offset each other. Or I'm sorry, not the area. The area, the integral, sorry, is -1 down there. Julie mentioned here, this looks like it's going to go the same way. He is correct on that. Let's go ahead and take the integral of the sine, which is negative cosine. Let's go from 0 to 2 pi. So I got negative cosine 2 pi minus negative cosine of 0. Oops, that's a 0. So I got negative cosine 2 pi is 1 plus cosine of 0 is 1. So -1 plus 1, I got 0. All right. So this area is, I don't know, let's say it's like, we'll call it 1. This area, or I'm sorry, that integral is -1, so they notice that they offset each other. But it's not the total area, right? We need to be careful how this question is asked, because if we had asked what's the total area, now that's totally different. That's totally different, right? So if we asked what's the total area from 0 to 2 pi, and I have the specific areas here. So this would be a 2. This one's going to spit out a -2, so we just take the absolute value. So it'll be 2 plus 2. Because remember, if I run an integral below the x-axis, it is taking f of x's that are negative and summing them all up, right? Summing all those rectangles up. So it's spitting out the opposite of the actual area. Okay. So what you want to do when you're finding total area is you want to think about, oh gosh, what happened? Think about if it goes below the x-axis or not. So number 1, find your zeros. Where are the zeros between 0 and 2 pi for this sine? So where's the sine function 0? And you're like, well, at 0, at pi, at 2 pi, and so on. Well, it's between 0 and 2 pi, of course, that's our a to b. So we're looking at that pi, right? That's why we want to visually, we're splitting this up. We're going to go from 0 to pi of the sine. And this will spit out a positive 2. Okay? And then we're going to go from pi to 2 pi. But we know this is going to spit out a -2. So we got to slap on the absolute values on this thing so that we get total area, not 0, right? Because if we just ran the integral from 0 to 2 pi, it would give us 0. We want total area instead. So we got negative cosine pi minus negative cosine 0 plus absolute value of all this stuff, negative cosine 2 pi minus negative cosine pi. Cosine pi is negative 1, plus cosine 0 is 1, plus we're taking the absolute value of this, negative cosine of 2 pi is 1, plus cosine of pi is negative 1. So we've got 1 plus the absolute value of negative 1 plus negative 1 is negative 2. So we got 2 plus the absolute value of negative 2, which is 2 plus 2, which is 4, is our total area. Total area, different question, right? Total area. All right, this one we've got x cubed minus x squared. Number 1, where are my zeros at? If I didn't have the graph, right, here's my function. Where are my zeros at? Where are my zeros at? At 0, at 2, and at negative 1. See them right there? 0, 2, and negative 1. That's where I hit. Those are all my x-intercepts there. Okay? And notice I'm positive between negative 1 and 0. So when I find the total area, I'll go from negative 1 to 0 of this function. And that'll be positive. Plus, when I run it over here from 0 to 2, this is going to be negative, so I got to slap those absolute values on it to find the total area, right? Because it's going to spit out a negative value for that integral from 0 to 2. Well, looks like I got negative a fourth minus a third plus 1 plus absolute value negative 8/3 is 8/3. Let's get a common denominator of 12. So we got negative 3 12s minus 4 12s plus 12 12s plus 24 12s. Let's do 5. Oh, sorry, 4 times 8, 32 12s. Good grief. 32 12s. So that'll end up giving us 37 12ths is that total area. 37 12ths. This next problem is a nice little introduction to the second fundamental theorem of calculus. So let's go ahead. Notice I'm taking the derivative on an integral. Let's go ahead and run the integral of the sine first. I know the integral of the sine is negative cosine, right? And I'm going from 4 up to x. So I throw the x in, and I throw the 4 in. So I have the derivative of this. And now I'm taking the derivative of that. Well, the derivative of the negative cosine. Derivative of the negative cosine. The negative stays there. I take the derivative of the cosine, which is negative sine. Take the derivative of cosine of 4. That's just a number. So I'm left with the sine of x. So what happened? Well, hopefully you see that the derivative and the integral, they undid each other, left me with the sine, and it throws that in. That's what the second fundamental theorem of calculus is saying, except I also give it to you in terms of the chain rule. So it's saying if I take the derivative of an integral, then the g of x goes in right there. So there's my f of g of x, but I got to run chain rule. I got to account for chain rule, right? In other words, I'm accounting for u substitution in terms of the integral. Okay, so when I run this, if I take this, here's my function. Oops, let me do it a different color. Here's my function. If I take the derivative on this, it'll undo it, and it'll leave me with t squared over t squared plus 1, but t squared is not going in. The x is going in for t. So x squared over x squared plus 1, and then times the derivative of x, which is just 1. That's the g prime part. So I'm just left with x squared over x squared plus 1. So in this case, it undid it. Let's do another one. Let's take the derivative here on both sides. So f prime, take its derivative. Take the derivative here as well. I'm taking this derivative. So it'll be sine of theta squared. But what's going in for theta? That x squared's going in. But don't forget, I got to take the derivative of x squared, 2x. So again, undoes it, but then take the derivative of that g prime that's going in. So this is just 2x sine of x squared squared, or sine of x to the 4th. I think a way to think about the average value of a continuous function is to introduce the mean value theorem for integrals. So let me talk about the mean value theorem for integrals for just a second. The mean value theorem for integrals states that somewhere between the inscribed and circumscribed rectangles, there's a rectangle whose area is precisely equal to the area of the curve. What do I mean by that? Here, let me see if I can't draw this. I go from A to B. Okay, here's the area under the curve there, as you can see. Imagine that being imagine it being 3D for a minute, and it being ice, okay? And if the ice melted, maybe it melts. Whoops. Yeah. And it's equivalent to this rectangle in red. Okay? And so this area under the curve is equivalent to the melted one, which has a height of f of c and a width from A to B. So B minus A is the width on that. That's the red one. It has the same area. Okay, that's the mean value theorem. Well, if you solve for f of c, so you divide both sides by b minus a. That right there is referred to as the average value of the function over that integral from a to b. In other words, let me go to the graph for a minute. From a to b, it takes on all these, in black, it takes on all those y values. There's an infinite number of y values. But the average y value is f of c. That's the average one, because I'm dividing it by the b minus a, the width of that, if you will, melted area of the rectangle. Okay, so that's where that comes from. That average value of a continuous function is 1 over b minus a from a to b. So if you want to find the average value of f, then you go 1 over b minus a from a to b of the function. You can find the average value of the function. In this case, we're going from a to b from 0 to 1 here. So 1 over b is 1, our a is 0, 0 to 1 of our function, and 3x squared minus 1 dx. So in this case, we just have a 1 over 1, so it really makes no difference with just a 1 out front. You don't always just have a 1 out front. Let's plug it in. Or let's integrate it and then plug it in. So we got negative x cubed. So it looks like I got negative 1 minus 1, which is negative 2. See, the average value of the function is negative 2. You know, if you were to graph this and go up by like 0.2, 0.4, 0.6, 0.8, 1, it kind of goes like that. I didn't draw that the greatest, but it's average. The average y value is negative 2. Right? That's what it's saying. Average value of a function. Well, thanks so much for watching. I hope that gets you started. That's the homework assignment. See you next time.